So today we're going to focus on the chemical processes of life. I basically set it up to where we're going to start with a review of what we covered this past week and last week, focusing first on atoms. And as you can remember, atoms are the basic unit, building block of elements and compounds. So an atom is the smallest unit of any element. We learned that an element can be composed of one single atom, or an element could be composed of thousands of atoms. Atoms consist of a positive nucleus, and then they have the negative electrons in the outer shell. Elements. We learned that elements are listed on the periodic table, and elements, when chemically bonded, form molecules or compounds. To know the difference between a molecule and a compound, we learned that molecules can be elements that are the same, such as O2 or N2, and molecules can also be elements that are chemically bonded that are different. And if they are chemically bonded that are different, they could also be a compound. So molecules, two or more that could be similar or different, those are molecules. If a bond is specifically joining different elements, that's going to be connection between the atoms are called bonds, and specifically chemical bonds, and they are based on the interaction, as we said, when those electrons collide and hit in the outer level. They may be stolen or they may be shared, and we'll talk about that. And so basically there's a large amount of energy given off to either make or break a bond. Now let's talk about those chemical bonds. Chemical bonds are a force of attraction. And we're going to talk about what those atoms want in order to be attracted to another atom. Bonding has a significant impact on the properties of compound. When the atom bonds, it will now have a new trait, a new character. We briefly talked about how sulfur is yellow and copper is an orange color. But if you chemically bond them together, they form a new substance, which is a blue crystal, which is copper sulfate. Now, in order to react, atoms will need to collide, run into each other, and that's specifically happening with the electrons. Now, the nucleus is never going to be involved in the bonding. Basically, we're only dealing with the electrons. And these are specifically the valence electrons, the outermost level. So the inner ones that are filled, they will not be focused on the bonding generally. They will not be focused on the bonding. It's going to be the outer electrons. Okay, there's your valence electron on the outer level. And that word valence refers to the combining power, the bonding of the element. And how does that happen? From the outer level. Now, something I want you to be aware of, the octet rule. Well, we just said what's going to create that attraction, what's going to create that atom to want to bond or link up with another. They want to fill their outer level. So they want to focus on completing a rule of 8. So they want to have 8 electrons in their outermost level. So if hydrogen has 1 valence electron, it wants to give up its electron so it could feel like it's going to get 7 more and have 8. Now, if you look at xenon or neon, a noble gas, they already have 8 valence electrons, so they will never bond with another atom. They will never bond with another element, because they are already filled, they are already complete. Oxygen, on the other hand, has 6 valence electrons, so it wants to steal 2 more. That's why oxygen bonds with hydrogen twice, to get H2O. And oxygen will take 1 electron from one hydrogen, take that hydrogen over, and then take another hydrogen's 1 electron and bring that over. So that's how we form water. And oxygen has 6 valence electrons. It takes 1 electron from one hydrogen, takes another electron from another hydrogen, making H2O. So that is the octet rule. The need or wanting to combine with other compounds in order to reach that stable um, limit or total of 8 electrons in their outer level. Now, atoms with less than 4 electrons tend to give up or lose their electrons, while atoms with 4 or more, such as oxygen, oxygen and carbon, they're going to have more, so they're generally going to take or gain electrons from other atoms. Now, xenon and neon and those elements that are on the right side, the noble gases, on the right side of the periodic table, they're already complete, so they will not bond. They do not bond with other elements. One way to help you visualize the valence electrons is the Lewis dot structure. The Lewis dot structure method is a way of putting the symbol of the element in the center and then identifying how many valence electrons. And those little valence electrons are identified by little dots. So you can see in the diagram, if it has 1 valence electron, we have 1 dot on the top right. If we have 2 valence electrons, 2 on the side, 3, we start moving around that element, okay, on the top. Then when we go to 4, we go to the left, and then 5, we go back down, then we circle around. So you can see the bottom left, hydrogen, 1 valence electron. Oxygen has 6, so it needs 2 more. So on the right-hand side bottom, you can see it brings in 2 different hydrogens to kind of steal their electrons while bonding. Now there's commonly 3 types of bonds, but generally in other resources and other textbooks, they include metallic bonds. So the most common are ionic and covalent. You may hear in different resources about hydrogen bonds, but in other resources or even on the internet, you'll read about metallic bonds. So I'm including 4, even though your textbook only covers 3. Ionic bonds, basically the focus is moving from one atom to another, moving or transferring those electrons. The atoms become positively or negatively charged. This is something you're going to see in chemistry. If you have an Na+, that's referred to as an ion. So basically they are more positively charged, while a chlorine minus would be a negatively charged ion. Now ionic bonds usually form between metals and nonmetals. So salt is an example of an ionic bond. This is when sodium, which is a metal, we learned that it's a silvery soft metal, bonds with chlorine, which can be a powder or a gas, a yellow gas. So it's a non-metal. Now covalent bonding is the key word there that you have to know for covalent is shearing. These bonds are generally more flexible and usually occurs between nonmetals. So the reason why they're flexible is because of the shearing that's going on. So one great example of that is water and carbon dioxide. So between nonmetals, so we have a hydrogen, which is a gas, oxygen, which is a gas, they bond together. Those are 2 nonmetals. That's a covalent bond. Hydrogen bonds are the weakest bonds, and these bonds have a slightly positive charge, and they're going to be attracted to anything negative. So they can easily be broken. Now the last one are metallic bonds, and these are bonds between metals, and basically because of these bonds in metals, that gives the metal a good property of conductivity, conducting electricity, and malleability. Malleability means being able to be shaped into pounded down, like I'm able to shape copper into wires, like a little cylinder strip. Now let's talk about chemical equations. You should have learned about this in 7th and 8th grade, especially when you learned about the equation of photosynthesis. Chemical equations are a shorthand of writing out, instead of writing out the whole word, we're using the symbols, and basically on the left of the arrow, we're going to be using the reactants. On the right of the arrow, we're going to be using the products. So If I'm forming water, the reactants, the things that are reacting together would be two hydrogen molecules and one oxygen molecule that come together and bond and form your two H2Os. Energy of chemical reactions. So basically, this is something that you should have learned in elementary school as well. An exothermic reaction is exo meaning exiting, giving off. So basically, energy is released. So a lot of heat is being given off. You feel something. Let's say we pour two chemicals together, and then we touch the beaker and it feels real hot. It's reacting, it's giving off heat. That's an exothermic reaction. Think of the prefix exo, means out or outside. We exit, we go outside. Now, a chemical reaction that is endothermic, endo meaning inside, just like when you learned about endothermic, you maintain your body temperature. That's going to be like 98.6 degrees Fahrenheit. Well, here in this case, endothermic is referring to energy is being absorbed, it's taking in. So generally it's going to feel cooler or colder. Now, something that will change the rate of reaction, that's going to be temperature, surface area, concentration, and enzymes. And enzymes, specifically an enzyme catalyst, will speed up a chemical reaction. So enzymes are specifically protein catalysts that basically increase the rate of a chemical reaction without the enzyme itself being changed. So the enzymes usually, when you take a chemistry class, it usually ends with ASE. So if you heard about DNA polymerase, that ASE is a hint that it's an enzyme. Sucrose is the sugar, sucrase is the enzyme that reacts with it. An enzyme will bond to a substrate, as you can see in the picture. So the enzyme here in the picture is going to be digesting or breaking apart the substrate. When the substrate attaches to the enzyme, that kind of opening, that you're putting the key in is called the active site. And then as the enzyme breaks apart the substrate, it forms the product. So synthesis is when the enzyme takes two different things and bonds them together. Think of synthesis like addition. And then digestion is breaking it apart.